Start with the lectures of Chris Fryer from Los Alamos. Electromagnetic constraints on the Supernova engine. Take it away. I'll get the bell. So behave.
Okay, so I'm glad that you thought I could behave. So that's excellent as a start. So Tony asked me to talk about electromagnetic signals, and that's it's a broad topic. I will try to start broad with a lot of examples, and then I want to do a couple examples where I narrow down and talk about what we need to do to get those tie the diagnostic to what we're seeing in the engine and all the physics that lies in between. This is a topic, so I'll give you the electromagnetic observer complaint about that when we talk about multi-messenger. There's a broad range of photons. These are different communities. So you don't usually have the radio community and the gamma ray community actually, well, they work together better than, say, the radio and the optical and the ultraviolet. So these are separate communities in themselves. You can't just say, I observed a photon and I've learned everything I can learn from supernova. There's lots of different probes in the electromagnetic range. And I will talk about some of these topics going from things like supernova remnants, so you can look at the observations from supernova remnants. You can also look at shock breakouts. So that middle plot there is one of the earliest shock breakout signals. It's also one of the shortest shock breakout signals we have. It's supernova 2008D. The remnant is Cassiopeia A, and it has the titanium observations on it as well. So it's both lines that are shock heated, that you're seeing the shock-heated material, which requires atomic physics and non-equilibrium atomic physics, but it also has radioactive decay signal from the titanium-44. And then on the right is a recent supernova light curve by Jillian Rastenijad. This was of an event that the Einstein probe got the shock breakout signal as well. And hopefully I'll cover some of that as on this. One of the things that so at Los Alamos, we are not typically funded to do astronomy. We have day jobs. My day job is a laboratory experimental person. So I model radiation hydrodynamics experiments in the lab. We do everything from shooting lasers at a target that makes a very hot material that then we follow the flow of that radiation down some target. We use Z-pinch, which is using magnetic fields to drive a pinch and heat up material to drive a target. We actually have people that take explosives and explode things and try to study the hydrodynamics. So we do a lot of laboratory experiments, and then we try to model them. What I've learned in 20 years of being a laboratory experimentalist, which I thought, moving from astrophysics to that, it was going to be trivial, because we actually make our thing that we're going to explode, right? We don't have to rely on nature making it. We make it, and so we know what we made, and then we try to learn. We blow it up, and then we try to learn from it. It has the same issues that we have with understanding supernova, in that there are still uncertainties. Even though we machined it, there's still uncertainties in the initial conditions. And then from then on, the uncertainties just grow, and it makes it very hard. So there's lots of, I've been trying to do the same physics study for 20 years. What we've learned is we need more diagnostics. So every time we do an experiment, we go, well, but why did it do that? So we add another diagnostic to try to constrain it. And so I've spent 20 years doing experiments, designing new diagnostics, and doing the experiments again. And I'll talk a little bit about that as we go through this talk. So with that in mind, that's where we decided, let's look at what we can use to constrain the supernova engine from all the diagnostics we have with supernova. And so you have the ones that we've talked about a lot today, which are things like, yes, sir?
It doesn't show up on the screen.
Oh. Is it not sharing?
It's probably sharing only the PDF, not like the.
Oh, okay.
Maybe I can.
I'm going to let you do that, and I'll keep on talking. So you have these diagnostics that you can do with in core collapse supernova, we have everything from most of what we've talked about this week so far, neutrinos, gravitational waves. Those are nice direct probes where you can see you're actually looking into the center. But then there's a whole bunch of less direct probes, things like the compact remnant distribution. That one, it turns out gravitational waves are also playing a huge role in that. We have observations from radio and X-ray of compact binaries, usually usually ones where you have something like an accreting binary or two binary neutron stars with a pulsar giving you the emission. That gives us some constraints on the masses, but you can also get constraints on the spins from the black hole spins observed from gravitational waves, black hole spins and X-ray binaries. So you can use that data to tell us something about the progenitors and also the explosion mechanism. Shock breakout, David Vartanyan has already shown us some simulations of that. That can help probe what's going on in the supernova engine and also tell us, as I'll show, tell us something about the supernova progenitor. Nucleosynthetic yields, there's lots of ways to get constraints on this. We have things like galactic chemical evolution, which is very indirect, but we have more direct things like looking at supernova remnants. All of these have issues with how you're studying it, but it's something that we can use as a diagnostic. And if you look at later, other observations, like you can look at the evolution of the spectrum and the luminosity. So we're going to get a lot more data with things like LSST. What can we do with all these observations? There's lots of ground-based telescopes on this. There's also, we're expecting telescopes in the UV, like Ultrasat, that will help us on this. UVEX is another mission that's going up. Depending on I keep on saying it's going up, like I envision that the funding is going to be flat and we're going to be okay. So let's assume that's true. So there's all these observations that we can be doing to place constraints on what's happening with either the supernova progenitor or the engine. And even though they're indirect, these are things that if we include with our full study, we will be better for it. And so let me just talk a little bit about this. Turns out that now. Yes. So let's talk about some simple questions that maybe we want to answer. One of them is, what is the supernova engine? So this group especially, I think we are in kind of the right mindset of what the engine is. I think for the bulk of supernova, it's this convective engine, but there's other engines that have been proposed, and I think they do make up some of the explosions. Kip Thorne came up with this, I call it White's mandate. It was from a book by T.H. White on King Arthur. And in this book, Merlin turns King Arthur into different animals and learns political systems from the different animals. And he was turned into an ant, and in front of the ant was something that said, see if I can get the quote right. That which is not strictly forbidden is mandatory. And the way Kip Thorne interpreted this is, if nature allows it, if nature doesn't strictly forbid it, it will find a way to make it. So if the laws of physics don't forbid something, it will happen. And so the idea here is, when you look at these different engines, say you have a disk-driven jet, so you have an accretion disk around a neutron star or a black hole. If nature can make that happen, if the laws of physics allow this to happen, nature will find a way to make it at least some of the time. Now, whether that's 5% of all supernova or 30% of supernova, that's one of the things I would like, I'm hoping that we can solve. The other mechanism so I work with the transient community, and they are much bigger on these magnetic engines. So magnetars have been invoked to solve everything, every explosion I've ever seen, until they get proven that they are not that. So magnetars are another one. I still don't understand the magnetar for normal supernova, because you can bury the magnetic field. We know this. We know this from recycled pulsars. So I don't know how the supernova engine doesn't bury that magnetic field, but that's neither here nor there. If you can make it happen, nature may have it. We want to see, can we prove which mechanisms are both the dominant one, which one, and then in the end, I would like to know what are the fractions of these different engines in our big set of transients that we observe. So that's one of the questions. The other is, what is our initial conditions? What is our progenitor? What can we learn about progenitor stars? And we've already talked a little bit about this, mostly making fun of the stellar evolution folk. It's how hard this is to do. And it's one of the big questions that we're trying to understand is, how do we do convection? And it's a really hard problem because you can model the 3D convection, but that's still not perfect, and you can only do a snapshot in time, and your viscosity, numerical viscosity, is too high. So it's not just, I solved this and I'm done. I think it's going to be an iterative process where we try to learn this, but can we place some constraints on what is happening with stellar evolution with this? And it's not just the convection. It's how are we putting in radiation transport in the stars? How are we doing mass loss? There's lots of different mass loss mechanisms. How do we understand this better? What really happens to the star as it evolves? And I think the interesting thing here is we had a period of time where the observations of stars were so poor that the toy models that we have were good enough. Now we know they're not. Now we have observational data saying we need to work harder. And that's the first step to then driving us to come up with new ways of doing this. And I think there's a lot of work to do there. But I want to talk about how we can use the electromagnetic emission from astrophysical transients to constrain some of our stellar understanding. And these are just, the images on the bottom here are using a mixing algorithm for stars, more standard for what engineers use. It's called a Reynolds average Navier-Stokes solution. Dave Arnett came up with it. And by putting that in, he changed how much, see if I can actually, he changed how much how much of the helium layer he produced just by putting in a different mixing algorithm. So these are different mass stars, but the helium layer got burned away because of adding this better mixing. And we'll talk about why that's an important feature as I go through the talks. So I've already said this. Gravitational waves and neutrinos are great. They're pretty direct probes. The problem is they're rare. The data is rare. So on the other side, the electromagnetic data, there's lots. But almost all of it requires a lot of underlying physics to tie back to the engine and learn something about the engine. And this is where Thomas Young said, there's no direct proof, and that's true. There's no direct proof, and the models are complex. But we actually now have a path, and I'll talk about that, of what we need to do and what we need to understand to take these electromagnetic observations and tie them back down to the engine. And so I think there's a path forward on this, and that's some of what I want to give today. We have had a lot of discussions on the physics of what you need to do, and this is a slide that Ray Fix made at the end of one of our time domain and multi-messenger meetings that we had, where he kind of outlined all the physics that you need to do to tie to these different observations. So we have all these observations that the observers are doing. I really can't use my pointer. Well, anyhow, you have all the observations that people are using, and like everything from LIGO and neutrino facilities to things like JWST and the different Ultrasat and all of these observatories. To do this, you need all this underlying physics. I think what we didn't appreciate so much in the electromagnetic side of late time evolution was we need more than just your simple, I do a photon transport, throw in my atomic physics and I'm good. The atomic physics is not well known. It's not just atomic, it's actually plasma physics because we're not at equilibrium. So the equilibrium solutions are bad. Dust is playing a role. So 230307A, which was a supernova, it was a long duration gamma ray burst, but it looked like instead of having a supernova associated with it, it had something that was shorter duration, looking like a kilonova. So people argued it was a kilonova. Unfortunately, it could also, the features that we saw could also have been carbon monoxide line was right at the spot where you could have seen it. It could be dust and atomic physics or molecular physics that's driving what signals you see. So you don't just have simple atomic physics. You may need molecular physics. You may need dust production. So all of that physics needs to be thrown into these studies. The thing that I would like to say is that we have a lot of laboratory experiments to help us guide that physics. So we're not just limited to what do we observe and then try and study it. We can go do laboratory experiments and try to understand this physics. So these are a set of the laboratory physics experiments that are developed, many of them to study a lot of so they call themselves laboratory astrophysicists, to study the physics that we care about and we want to improve on. So it's a rich field, but we're not on it alone. We have a broad physics community that will help us on it. So let's talk about one of the kind of the diagnostic that kind of I felt really sealed my view of whether this engine that is our standard engine that we're looking at, where we have these convective instabilities that grow and eventually drive an explosion, is the right engine, or at least one of the engines that exists, is Cassiopeia A. And I'll tell you the story on this Cassiopeia A. If you threw away the blue image, which is titanium-44 decay lines, so from NuStar, if you threw that away, you would have this feature, this green feature, which is silicon, and you would say, it looks like a jet. And in fact, we did an observation with the Chandrasekhar telescope. So with Chandra, we did an observation, and all of the observers on that paper wanted to claim that this was a jet. All of the observers. The only people in the paper that did not like it were the theorists. And we kept on arguing, well, that silicon feature you see, it's not just the motion of the material. You're seeing what is shock heated. When you look at the silicon, you're seeing only what is shock heated. So if you had, there had been models of this, if you were blowing this up into an asymmetric surrounding medium, you could get an asymmetry in the shock heating, which would then cause this silicon feature. So we then went and said, well, what's the solution? How do we solve this question of whether that's real or not, that silicon feature, that green image you see? The way you would solve it, one, is to then ask the question, what does the titanium look like? Because the titanium is made down near the engine, and we'll talk about this in more detail. The titanium is made down near the engine. If the engine is really that aspherical, the titanium should be aspherical. And it is not, it's not spherical, but it's not a jet. You see it. The titanium, it looks like it is multi-lobes blowing up. And we saw already some simulations that match this. But the prediction we told the NuStar team this would have been in 1998 when they were first designing the NuStar mission, is if we were really right in what we thought the convective engine was, this is what they would see something along these lines. And when we saw this to me is proof that it's not just a single jet that's driving it. You can argue that you do have, maybe that silicon feature is caused by a jet that happens after the explosion, doesn't contribute much to the heavy element production, but you do have to come up with a way to do that. And I know there's people that have come up with ways to make it work without a jet, with a jet. But bear in mind that you can also explain this still with a aspherical circumstellar medium. And that's what John Blondin would argue this for his, when he did his thesis with Roger Chevalier. So it's a long known problem. So we have this data. If you just looked at the X-ray, you would have thought it had to be a jet. When you added like low energy gamma rays, which NuStar is, you see that it's probably more like a convective engine. And now we're looking in the infrared to look to see where is the iron that's associated with that titanium, because there's titanium where there's not iron, and that's really hard to do. It's just at the edge that you can do titanium without much iron. There's a couple ways to do it, but that's what we're studying. So that's one of the things you could study, is say, oh, I need to understand nucleosynthetic yields. So let's go and do this. Magkotzius did a detailed study where what he said is, I'm going to take material, let it get shock heated to some hot temperature, and then I'm going to cool it. And so we want to do a lot of calculations, so he chose a simple model for that shock heating. He said, I'm going to make it really hot, and then I'm either going to use a power law or exponential decay in the temperature. And there's also people that do models where you start with an exponential decay and then you go to a power law. There's lots of ways to do this. He did that kind of modeling where he shock heated it and then let it cool. And he then said, I'm going to shock heat it to different peak temperatures and different densities at that peak temperature. So the y-axis there is the peak density, and the x-axis is the peak temperature. So each of these little color, everywhere on this graph is a different, he did a different model where he went to this peak temperature and density and then let it cool. And in all of these, he then asked the question, what's the titanium yield? What's the nickel yield? And it gives you a really good idea of what the physics is. So if you look here in the titanium, there's this kind of, you see this point where it's there's like a kind of valley. So that's a place where the titanium gets destroyed really easily. There's places where the titanium is made in abundance. The points on this are different 2D models, the distribution of peak temperatures and densities from those 2D models. So you can then look at it and say, oh, I get a lot of titanium yield. That tells me something about the peak density and peak temperature of the explosion. So we can actually use the yield to get us some ideas of what did the shock really look like. And we're doing this not just with titanium. Nickel, you can see, is not as sensitive because you make a lot of nickel no matter what you do. But there are a set of elements that you can use as probes of exactly what's the peak density and peak temperature of the shock heating. And that would be great if that's all you had to do, and that was the models work like that. And we've done things like that. We do things then, and we can take those yields and say, what do we observe? So for nickel 56, we looked at 1987A and said, okay, what was the gamma ray signal? Well, for some reason with 1987A, the gamma rays were the gamma rays were redshifted, so they were moving away from us. So the gamma ray decay line was moving away from us from nickel 56. What this required then was that you had a lot of nickel going in one direction, and we're seeing it as it's moving away from us. Oops, sorry. We were seeing it as it's moving away from us. So we can observe the gamma rays from 1987A, and we know it has a very strong explosion in one direction, moving away from us at roughly a 45-degree angle. This plot shows that nickel distribution. So the red is the nickel distribution in the explosion. And then the different curves on this plot are looking at the nickel from different angles. So the kind of image that we end up observing is the image on the bottom right here. That's what we ended up observing. So we were kind of looking away from the nickel. The nickel was moving away from us, and that's what we saw. So that observation alone tells us that we had an explosion that was stronger in one direction. And it was moving away from us, and so we know even what the asymmetry is. So it tells us something about the asymmetry in the explosion. And the nice thing about nickel is that it's fairly robust. It's not that sensitive to the nuclear physics. But the materials that are sensitive to the nuclear physics can give us a lot of information. If we had a galactic supernova, so say we get one where we get the neutrinos, the gravitational waves, because it's galactic, it's near enough, we will also get a whole slew of detailed gamma ray signals. So we won't be limited to just what is the nickel 56, what is the titanium 40. There will be a whole slew of radioactive isotopes that are sensitive to different aspects of the star. So on this left plot here is the enclosed mass of a star, and the Y is the flux in photons for different gamma ray lines. And sorry, this is the enclosed mass, and this is the amount of iron 59. So it's one of the elements you make. If you're slightly neutron rich, you can throw some neutrons onto iron 56 until you get up to iron 59 and make a set of radioactive isotopes. You can also do it by doing some alpha P captures and and building things that way. So you can do it in a number of weird ways of making these elements. When the different curves here are for different explosion energies. So if you take a star, hit it at different hardnesses, you'll get a different yield. So in this case, these are all 1D explosions. The shock initially destroys the iron-59, but in a shell-burning layer, it actually creates iron-59. So you can go look for this iron-59 from neutron capture and study what is the composition and nature of that shell, and also what is the explosion energy. So it gives you some observations. If we had a galactic supernova, instruments like COSY, which hopefully will get launched in 2027, 2028, we'll be able to observe these lines, and we can probe them. The strength of the line also depends a little bit on how mixed you are. So there's a lot of different degeneracies in what you see, but this is one of the observations that we can tie to. So if we do this framework where we look at the explosive engine, we look at so we have the explosive engine, we have properties of it, we look at the progenitor and have properties of that, we can tie that all together and make some nice models. The problem with this physics is it's non-trivial. There's lots of uncertainties. And here's the kind of pipeline of how we have to understand these physics models. We have to go from the microphysics all the way to the explosions. We have problems with the fact that we don't know the reaction rates that well. So we have nuclear experiments. And this is Kelly Chips at, I think, Oak Ridge. I think Rafe Hicks was on this study looking at alpha capture on the titanium-44. So it's an alpha P reaction. You throw that into that gives you some measurement, but you have to tie that within a nuclear physics model. And so the kind of brown curve is what you would get if it was the nuclear physics model by itself. When you add data, that constrains the error. So this is the reaction rate is uncertain by almost 2 orders of magnitude without any experimental constraint. That's because Hartree-Fock and different nuclear physics models are not perfect for us. So the different models that we use for the quantum physics are limited. So we have these limited quantum physics models. We use experiment to help constrain them, and then we try to get better reactions. So that's an uncertainty we have to include. There are still differences in your nuclear networks. Different nuclear networks get different answers. Those are actually small. These are different nuclear networks calculating the same trajectory, same reaction rates, and they're getting different answers. Why? Because how you implement the reaction rates can be different. Electron screening can give you different answers. So you have to get that physics correct. The errors here are more like 30%. So when the nuclear reaction rate is a factor of 100 error and the network is only 30%, you can ignore it or not worry about it as much. Trajectories are also a problem. So I told you that Mercatius assumed this simple power law decay in the material. That's not what we see in modern multi-D supernova explosions. So you have to do that right as well. I'm just giving some examples. And then you tie to the gamma rays. So that's kind of the path to getting all the way to the gamma rays. Right now, the uncertainties are fairly big. This is the whole part that is fairly indirect. But we are doing a lot of work to study this. So we've already had a meeting where we discussed what are the uncertainties. We're coming up with plans of how do we beat those down. So here's just a little bit more detail on the kind of concerns we have with doing the nuclear physics. The first is that power law good enough? The answer is no. The power law, the simple power law temperature evolution here, so this is temperature versus time. The simple power law temperature evolution is that blue dash curve. The solid lines are actually from 3D explosion models. Then the other dash curves are if I say the material is slowly decelerating, which we typically don't put in our models. But if you have it slowly decelerate, which you would expect as materials moving through a dense medium, that gives you a better fit to what our 3D models are giving. So that's one physics thing that we have to overcome if we're using these little toy models. And you know the deceleration, when it decelerates and when it accelerates, by understanding the structure of the star. So it's not just what is your explosion model, it's what are you using for the structure of the star. So this is if you've ever done your set-off explosion, you know that a shock will decelerate if the density falls off more gradually than r to the -3, and then it will accelerate if it's falling off more rapidly than r to the -3. And so oftentimes stellar modelers plot rho r cubed, and where that's flat is when it's right at the boundary. It keeps a constant velocity, and then if it's going up, that's when you would be, that would mean you're slowing down, and if it's going down, that's when you're accelerating. This is looking at a particular set of stars, and it turns out where the convective modes are, the blue shaded regions are convective regions. So there's ways to kind of get a guide of how does the density evolve, how does it behave as a function of convective regions and all of this physics. So we're studying that, trying to understand that, so we understand how is our progenitor affecting the evolution of the trajectories. The other thing that's a big aspect that we need to worry about with the evolution of the trajectories is the fact that the engine doesn't really turn off once it starts exploding. It explodes and material keeps on falling in, driving more outflows, and those outflows will catch up with your ejecta, and they can accelerate that. So these are models by Sieverding studying that, and so you have to include that physics as well. So we have those models. Then you get trajectories that look something like this. So the top is modeled by Sieverding, the bottom is one by Wang and Burroughs. And so you get models that you have to worry, that are, the material temperature doesn't just cool, it cools, heats up, and can do a lot of weird features like this. But you should also be concerned with just taking a 3D model and using it. There is no way, if you look at the Wang and Burroughs as an example, but there is no way that the trajectory is doing this. That is almost certainly a numerical artifact. So you have to know when is it a numerical artifact and when is it real. So you can't just grab your 3D model and say this trajectory is perfect. The way we're going to solve this is you take the 3D models, you take our 1D understanding, you take our analytic understanding, and you try to come up with realistic trajectories so we can understand the uncertainties. So this is not a solution that you can do just by doing a better and better 3D simulation. I mean, and if you didn't already know this, so most people have done, you make your 3D hydrocode, you do the set-off solution. It's analytic, it's exact, your model should match it. These are the tests of the flash code on a 3D explosion analytic. The solid curve is the set-off solution. It is what you would get if you could get the high enough resolution. The dots are what you're getting from the calculation. Why you should worry about your 3D calculation is look at the top, look at the pressure. So the pressure is AT to the fourth. In this case, it's probably radiation pressure dominated. Look at the pressure versus what the code is getting. Now, let me tell you that a lot of the nuclear burning is sensitive to the temperature to a very high power. If your 3D calculation is not capturing that shock heating, you will not get the right yields. So again, I think the way we have to do this is you need the 3D calculations. There's no way you can get around it, but then you have to tie it to a physical understanding and actually do the, combine the 3D calculation with an understanding of what the analytics and what we see in the 1D models, and couple that all together into an understanding of the physics. There's a lot of tricks to try to capture the shock better, and you could. That's another approach. I will tell you that's a big effort at a lot of the national labs, and it's not a solved thing either. But you can use better techniques than just simple AMR to try to solve these things. That's just getting the trajectories right. Then you also have to worry about the physics. And I've been asking about what's the electron fraction all the time. It's not just in the getting the electron fraction right to understand what are my heavy elements getting produced. Even things like titanium-44 are sensitive to the electron fraction. And maybe just look at the top curve here. This is the titanium production. We decided to study how sensitive is the titanium abundance to the electron fraction. The solid dotted and dashed curves are 0.5, 0.508, and 0.52. And even changing the electron fraction from 0.5 to 0.508 reduces the total titanium production by almost an order of magnitude. So your neutrino physics will affect my titanium yield. So it's unfortunately sensitive to that as well. So this is where we, it's not just getting the engine right, but it's also getting the neutrino, like not just getting what's the strength of the shock right, it's also getting what's the electron fraction correctly to do these yields. So there is a team that's a kind of international team set up to try to beat down all of these uncertainties as far as what do we need from the different communities to actually do these studies. And then the last is what's the sensitivity to the actual things like alpha capture reactions. So I thought before we had this meeting that we knew alpha capture. This is alpha gamma, alpha proton capture. So you capture an alpha, emit a proton, and that builds up, or you capture an alpha and emit a gamma, and you're building up your elements. So my dumb picture of how I made titanium-44 would be I just throw a lot of helium atoms on each other until I build up to titanium-44. Okay, that's great. That's not really what happens for titanium-44, but in addition, those alpha capture reaction rates are really uncertain. So this is just assuming the trajectory is known, assuming everything else is known. This is just varying our uncertainty in the nuclear physics, the reaction rates. This is the uncertainty in the titanium, and so this uncertainty is also 2 orders of magnitude. If you took maybe the 1 sigma there, it's still over an order of magnitude variation in the titanium production. So there's a lot of work that has to be done here to actually constrain these results. And I think this is where I would like to stop the first half of my lecture. I think the main thing I wanted you guys to get out of this first part is we have lots of observations. We have lots of diagnostics. But those diagnostics are all like this nucleosynthetic yields, where they depend on lots of pieces of physics. They need both lots of astrophysics input to get what are the explosion properties, what are the stellar progenitors, but there's also a lot of nuclear physics that we have to add into it. And the way we're getting around this is we're doing laboratory experiments, we're doing nuclear theory, we're trying to combine them, and we're trying to do what you would look at as a complete system study of what are all the uncertainties, how do I combine them, and then that gives us an approach to how we will beat down on those errors. So as we do this, we will start beating down on those errors. And then I think you get to a point where these other diagnostics, they're still going to be less direct than what we can do with neutrinos and gravitational waves, but they provide a different window into what's going on to both the explosion and the progenitor, and I think that can give us a lot of constraints on the observations, on the engine properties. And with that, I'll stop my first lecture and take some questions.
Thank you, Chris. This was very nice. I personally learned many things. So we have time for questions from the audience or online. Don't be shy. Yes, Matt.
So you say supernova engine. What's actually the difference between supernova engine and explosion mechanism? Is it the same thing, or?
So I think of it as, I'm thinking of it as whatever the explosion mechanism is. So for me, the supernova engine is it a disk that builds up a magnetic field and gives a jet? Is it a magnetar? Is it this convective engine that we're kind of using? So yeah, I'm thinking that's what we're trying to constrain with these observations. There is a confusion in the transport community, or sorry, the transient community, where they call it engine driven, and for them, engine driven is a disk for some reason, and then so it's engine driven or neutrino driven, which maybe they're thinking because it's a disk and it's winding, it's an engine. I'm not quite sure, but when I think of the engine or the explosive mechanism, I'm thinking of the same thing.
Okay.
Chris, thanks for the magnificent talk. So, you know, one of the things that was compelling to me, obviously, is the connection, the sensitivity of titanium-44 to the neutrino transport. I mean, that's a bad thing and a good thing. I'll talk about it as a good thing. So, the sensitivity to the YE in particular, and then the sensitivity to the transport scheme. How good how good are the observations, in other words, in pinning down the electron fraction? You know what I mean? There's uncertainties across that wonderful linked chain, and I'm just wondering if there are uncertainties that are going to get kind of muddy the waters a bit in the ability to use these observations ultimately for modelers to constrain the neutrino transport. Does that make sense?
So, you know, right now the data is not that good, right? So we have Cas-A is where we have a good titanium-44 abundance. COSY will do Cas-A again. It will look at a couple other supernova. So we have, you know, hints on supernova 87A for its total yield, and if we could get the line features, we could get something about the asymmetries in the titanium from that. But right now we don't have that much data, and again, then we have all these uncertainties. So you know, you can't just say I observed the titanium and I'm done. But if we had a galactic supernova, I wouldn't, even in the radioactive isotopes, I wouldn't just have nickel-56 and titanium-44. I'd have all these other isotopes, and I could use them to start to put together this detailed picture of what must have happened. So when you have, you know, when you have 10 unknowns, you're going to need 10, you know, and because none of the observations are perfect, you need at least 10 observations to really kind of constrain that. But we're going to start getting that if we have a galactic, so in the world, because it's today, right? We're getting a galactic supernova today. I'm looking at.
It was last night.
Oh, it was last night, yeah. Yeah, well, better at night than at today, because then we can get the observations, yeah. But okay, so we have, you know, when we get that galactic supernova, the data we'll have from radioactive elements, from the light curves, and I'm going to talk about the light curves in my next lecture, will be so much that we'll be able to start putting some constraints on this. But again, we're in that situation that you are with gravitational waves. We need to get that pipeline. We need to do those studies so we're ready to actually take advantage of that data. So I think when we get that galactic supernova, we will be able to, this will be where we'll have enough data. If we have thought it all through and know what we should be observing, we will have enough data to put the constraints on it. And I think that will really help us.
Another question. So first of all, thanks for the wonderful talk. You hinted in a couple of parts, but I was wondering if you can summarize, and if you're going to cover in the second part of the talk, it's fine. But I was wondering if you can say a little more about if there would be differences on the observation of electromagnetic signature, if you would have a rotating progenitor or a non-rotating progenitor, just because sometimes we ponder if we would be able to distinguish from the gravitational point of view, is there something in the electromagnetic point of view that could help us?
Yeah, and so I'm going to talk about that a little bit in the next talk as far as light curves. But you know what you would have seen in the supernova remnants as well. If it was a jet-driven explosion, we still need to make sure we're doing that detail right. The titanium-44 should have been also jet-like, and it's not. So I think you'd have it's a really tough argument. And the way the jet people are getting around that right now is, if you've heard of the jitter jet thing, if you make the jet do this, then it's hard to distinguish a jet from the titanium. And it could be that even if the disk wind is dominating the titanium, you can also somehow make it look like this. But I think that is the struggle to say Cas-A is a jet-driven explosion would be in that titanium already. And I'm going to talk about other I'm going to talk about shock breakout and light curves in the next lecture. And I think there's evidence there where some explosions clearly have a more jet-like structure than others. And that's, I think that's probably giving us the clues of what is jet and not. Again, if we had a galactic supernova, or even if with enough Virgo supernova where we have, this is where it would be really nice, again, gravitational waves, if it's rotating really rapidly, we will know, gravitational waves will provide really good insight, and that we'll use that to help calibrate our electromagnetic signals, I think. So I think that would be the other way you can do things is you're using the highly studied ones to calibrate how do I interpret the tens of thousands, hundreds of thousands of light curves that we observe. Because when it comes to studying populations, we're going to be limited to the electromagnetic. It's the only one where we can study real numbers of populations, where we get hundreds of thousands of data points to study populations.
Any other questions? I actually have a quick question. When you mentioned about the trajectories and the reheating in the shock, setting aside all the details of the simulations and so on, what are the main mechanisms that will cause this reheating of main physical mechanism?
Yeah, this was one where I was thinking it was some complex nature of converging shocks that was causing the reheating. And we were sitting there looking at the simulations, and then we realized, no, it's much simpler. So, I was making it, you have these 3D explosions, you can get some convergent shocks that then they're kind of, so you should expect when these blast waves go out, if they were spherically symmetric, fine, you have a forward shock, you have a reverse shock, that's all you get. When the complex, the stars are not spherically symmetric, the explosions are not spherically symmetric, you're going to get weird complex shocks. But the other one that I think is probably more important is the fact that the engine, you drive an explosion, but you're still getting downflows and outflows, and those can catch up and cause some heating. So we have some good examples where we looked at in detail at the simulation, and we watched the leading material that was cooling down get hit by material that was behind it, and that's that at least for a lot of these features that we're seeing is also very probably more dominant than my complex shock structure one. But both are there. We know this kind of complex shock heating is there as well because we see it in the early time light curve. So I think both are happening. But it may be, especially for stuff that needs to get quite hot, in a few times 10 to the 9 Kelvin, like the titanium, it's the long-lived engine. The engine not being done, it's still having fallback and material hitting it. So that I think these are, as we disentangle it, it's sensitive to that, but then I like to look at it on the good side as well. That means we have a way of probing that kind of long-lived evolution of the engine. So I'm hopeful that if we can do good enough models, we can actually tie to all this interesting physics.
Thank you. Well, we are just in time.